am going to get going. And per my remarks just now, what I'm going to be speaking about is this interface between, on the one hand, system science and dynamic modeling, which has been really the focus of this course, and data science. And it has to do with understanding structure in the world and relating that structure to our understanding of systems in the world that are giving rise to that data. If we think about data from the world, I'm at once a data scientist and a system scientist, and I spend a lot of time directly and through my students with data that exhibits complex patterns. Some of this data we collect from smartphone-based data collection, some from observations of case counts, for example, in the world, some from data regarding environmental sources, be they weather, temperature over time or precipitation, what have you. And that data exhibits complex patterns. Sometimes those patterns can seem all over the map, very entropic. Sometimes they can seem to have some structure to them, some regularity, some orderliness. But pinning down what's the significance of that is challenging. And generally understanding data, making sense of it, drawing insights from it, using it for filling in guesses for values you don't have, what is called prediction in machine learning, is a big area of current study. Much of what this class has been about, though, is really about what will be called statistically the data generating process. But it's really the fact that when we see data from the world, it generally arises from some sort of complex, typically coupled, evolving nonlinear dynamical system. Now, those are big words, a big mouth. But I hope that you'll have some sense from this class as to some of the things that are involved. Dynamical system, a system whose evolution over the next little bit depends on its current state, depends on what is now, determines how things will change over the next little bit, right? The value of the stocks determines the value of the flows. Or in an agent-based model, the distribution of agents among their various states, thinking their state charts depend on what happens next, right? If we have a lot of susceptibles and a lot of infectives, that's a recipe for quite a bit of infection. But if we have no susceptibles and no infectives, there's going to be no infection. So the current state of the system is going to dictate its evolution. That's a mark of a dynamical system. These are nonlinear systems. We need both susceptibles and infectives, for example. You need two to tango in order for there to be infections. You can't break up a system and to just analyze it for susceptibles separately, just analyze it for infectives and add the results together and expect to get insights on what it will be with them together. They're coupled. So what's going on in the system with predators, with the lynx in the boreal forest, is going to impact what's happening with the hares, the snowshoe hares. And if what's going on with the snowshoe hare population, if due to some disease or other predation, snowshoe hares are in short supply, it's going to affect the predators. We're dealing with coupled systems. And they're evolving over time. They're changing over time. And the data we observe from the world, data that involves real problems in the world, generally arises from those sort of tangled, complex, at a technical level, systems. And within our class, from the perspective of modeling, we talked about this construct of a state space. You may remember some of our depictions of state space. right? If we had a model like this with susceptibles, infectives, and temporarily immune people, we might see an evolution in state space, in this space where each axis is given by the value of some, in this case, stock, the state of the system. And it can evolve in a trajectory over time, where as those stocks changes, its location and state space changes. And in this case, it's going to some sort of equilibrium, some sort of balance point within it, where, well, if it's a stock flow model, inflow equals outflows for all stocks, right? The derivatives of all stocks are zero. So we saw this construct of a state space. We saw that, particular trajectories of the system give rise to these trajectories in the state space, right? But when I was describing that, as often happens in teaching, I was trying to simplify to get to the essence of the issue. And the inquisitive among you might have made note of something. I mean, there's three state variables here in this model, right? There's three stocks, right? And at a basic level, you might think, okay, to summarize the state of the system, to characterize its current state, we need, therefore, three numbers. One number for number of susceptibles, number of infectives, and number of temporarily immune. But if you actually analyze the state space, which you might think, I mean, it's certainly depicted in 3D, you analyze it from the right angle, what you actually find is that it's actually not a 3D structure intrinsically. It's a two-dimensional structure. It's kind of planar. It's as if there were a piece of paper sticking out of the board, going into the board here, right? And there's kind of a spiral on it if we look from another angle. But it's not occupying three-dimensional space. It happens to be embedded and it's sitting in three-dimensional space. It's actually a 2D surface in three-dimensional space, much as this piece of paper is essentially intrinsically a two-dimensional surface in 3D space. And I might bend it a bit and I might curve it, but intrinsically, it's still a two-dimensional, what we've called manifold, embedded in 3D space. Its degrees of freedom, its sort of modes of flexibility are really limited to two dimensions. And you could characterize its state based on a certain number of how far it is this way and how far it is that way. Now, by contrast, a system which, and looking for the reason for that, you might say, well, wait a minute. I mean, there's a conservation of people here. I mean, S plus I plus temporarily immune is equal to a fixed value, the total population, and right you would be. And that conservation leads to this smaller intrinsic state space. If we had a system which had new arrivals, be they immigration or births or mortality, we might see something that occupies closer to the three-dimensional state space. But here's the thing with which I want to whet your appetite a bit. When we look at data from the world, we often see patterns in that data, which we can relate to what comes out of a model. And if I told you, well, what we see from the world in terms of infection curve mirrors what we see out of the world model, you would say, well, that makes sense because that's why we're building models. It's to provide that. But what I'm saying is the data coming out of the world, if we use the right lens for it, it often actually reproduces not features over time that we see only. It reproduces features of the state space. Those sort of loops that you see, et cetera, the sort of arrivals and an equilibrium. With the right way of viewing data from the world, we'll see similar structures emerge from that data with the right lens. we look at data from the world with the right perspective, as it were, with the right way of summarizing it, we'll see great regularity in those systems. And what I'm going to tell you is that those regularities, this one from noise applied data from Saskatchewan, from our own province during COVID-19, successive waves. This data actually mirrors in many of its salient sort of features. If we use the right lens for it, what we see out of state space. And here's the thing, that's not an accident. It's because it provably recapitulates it provably. It provably shows a structure which is provably a sort of just a stretching of the structure, the underlying state space of the system that gave rise to it. Let me say that again. The data from the world, if we view it with the right lens, we view it with the right summary method, we can see, put on the right goggles, as it were, we can see the features of the state space of the system that gave rise to it. I'm not saying anything about a model. We may not have a model. We may not have built a model. I'm saying if we had data from some complex system in the world where we might not have done any model, and we put on these goggles, you know what these goggles are, they're mathematically proven. And you look at this data, you can actually see the key features of the state space, of the underlying system, the system that gave rise to it, the system out there in the world, which were we to build a model, we'd want to try to reproduce those features. We'd want to build a model that has similar state space. But I'm saying we have a way of peering into the state space of the underlying system, of the system down here that we generally can't observe directly. All we can see is little bits of data coming out of it from this part of the system or that part of the system. Maybe we're lucky and we have case counts collected for us. Or maybe we have some information about the snowshoe hare populations for certain years from the markets and the paw. Or maybe we have data from a hospital on the number of people in the ICU and the number of people in the wards, but we don't have admissions, we don't have number of deaths, I don't have number of transfers from the general wards, the ICU, or what have you. But it turns out using, and this is the more remarkable thing, even one piece of data, time series on one piece of data, can allow us to reconstruct that state space. One piece of data. And the key point here, I'll be expanding on this, but the key point is that in these coupled systems, in that system of hares and lynxes, snowshoe hares and lynxes, in that system of how COVID spreads in the community, in that system involving how wildfires spread, that in that system, there's so much interdependency from one area to another, from the availability of snowshoe hares on the lynx population, that having data about one part of the system gives you the information about the other parts of the system that are entangled. And so it's not a matter of just being helpless unless we have data from all across the system, on all of its different state variables, of where we only to know them. No, data from just one thin sliver of the population contains information about the other parts of the system entangled with it. And if we just know the right goggles to put on, we can see that information. Okay. So my comments here are going to need to be abbreviated because of the time, and we have to get on to a class wrap up. But I do have some time afforded for the next 35 minutes or so. And I want to expand on some features of this. We talked about state space within this class in the context predominantly of stock and flow model, dynamic models, right? And within that context, I introduced flow lines and we talked about how trajectories evolve according to these flow lines. You may remember I'm showing here like one axis for one stock, another axis for another stock. It turns out that if you have a much more high-dimensional system, like the system we might characterize with an ABM, if we were to take data from an ABM, you might think, you could be forgiven for thinking, based on my past comments in this course, and it's true, that the nominal dimensionality of the state space associated with an ABM, the number of possibilities that ABM has, if you have n people in the population, capital N, and each people, well, imagine each person could only be in, I was going to say 3 states, but I'm going to make it simpler because we're computer scientists here. I'll say 2 states. We had n equals 10. How many possibilities are there of states the entire system could be? Good. I welcome suggestion. The first person can be either of 2 states. The second person, factorial is like if the second person were somehow constrained because of the first person situation. Normally, that's not the case. So the second person could be in either of 2 states. The third could be in any of 2 states. The fourth. So it's 1,024. You demand. Okay. 2 to the 10, 2 to the n. Right? Because it's 2 times 2 times 2 times 2 n times, right? That's what 2 to the n, right? It grows geometrically. It grows. You can be forgiven for saying exponentially if you consider n as like a continuous variable. But here's the deal. The actual intrinsic dimensionality, the actual fraction of that possibilities that are occupied are much smaller. Because a lot of those possible states the system can be in are vanishingly unlikely to be around or persist. Whether you're infected tells a lot about whether I'm infected, particularly for those in the front row. And so when we have a system with a lot of coupling, it may seem like it has just a vast array of possibilities. And that is true at a certain nominal level. Sort of in theory, it has a vast array of possibilities, but because of the coupling between them, let's say between hairs and links in this model, which a version of which you ran with AnyLogic, right? It's one of the built-in models with AnyLogic. The green are hairs, the red are links. And they move around in random walks, and the links, if they're not able to catch a hair after sufficiently long, they die. And if hares have the misfortune of running into a lynx, they die. Now, this induces, and you may remember this, over time, aggregate behavior summarized up that exhibits some high-level features. You may remember for the model of predator-prey there was a stock flow model. It exhibits cycles. Do you remember that? Do you remember that? Perhaps it's been too long. Perhaps it's been too troubling the semester. But you may remember we have a lynx and hares stock and flow model. There were these oscillations. The growth of the hare population would mean the fact that hares are growing quickly would allow lynx to start multiplying more quickly. They could have larger litters, more of their young would survive, more of them would reproduce in the first place, would give birth, and that led to the lynx population growing. And the lynx population growing would then put a cap on how far hares could grow and would start it turning over to where it maxes out and then starting on the downward path. As lynx are numerous and there's fewer and fewer hares to go around. And that, like the night follows the day, would lead to lynx population maxing out. But we see the same behavior recapitulated in a stochastic way from a model of lynxes and hares over time. But if we look at the state space, if we were to summarize up a version of the state space, so we had a count of hares, a count of lynxes, and the x and y axis respectively. What we would see is not dots all over the set of possibilities, all possible counts of lengths with all possible hares. No, there's some structure to this, some quasi-equilibria that the systems go through. I say quasi because it's not going to a certain point where the number of hares and the number of lengths are in perfect balance. It's sort of cycling around them, which actually happens in the stock flow model too. But here we can see sort of two big basins of traction. I think I misspeak. I actually changed the parameter there and it went from one to the other. I will note that we see these sort of patterns in very high dimensional systems with lots of agents of many sorts. This, I believe, was from a model of communicable disease spread, where we see two different equilibria associated with it. For a model of spread of infection and networks, for example, if we were to summarize up the number of people infected now and the number of susceptibles, we would see a sort of what seems to be an attractor with some behavior around it, some stochastic behavior. And it would induce some high-level patterns. It's a data-generating process. In this case, like a relationship between income, which has to do with the crowding level, and the number of infections people had in that model. That shows more infections among people of lower income due to crowding. And there might be some separation for those who are high socioeconomic status. So, for example, with high incomes or lower incomes there on the left, there can be some divides. But these are high-level summaries that capture regularities. They capture the fact the system is not all over the map. You might think, well, there's thousands of individuals. It's going to be, occupying all of these different possibilities of the system. No, there's regularities. There's so much going on in terms of coupling between people and how it's spreading in the network and how one person is impacted relative to another. If this person sneezes, that person's going to catch a cold really soon. So when we have these systems, nominally they may seem to be a higher dimension. But in fact, if we take a critical lens to it and we examine it through the right angle, as it were, speaking metaphorically, with the right goggles, using another metaphor, we'll see the dimensionality is a lot lower than we would think. The essential features we see coming out of these systems, because of the coupling, because people here are very closely entwined with their health status with people here, etc. There's really big regularities, big order that lies behind this system. And it turns out that if we start to use the right lens even more, we'll find that, wait a minute, like the lynxes and hares, the patterns we see over time, if we were to plot out like lynxes now versus lynx a day ago, that's what's in the lower right or upper right, hares now, hares a day ago. We see them, in two lines that look awfully similar. I mean, they're different in their values. There are fewer lengths in the lower one, like 700 here versus 5,200 hares there. But they look very similar, and it's not an accident. So what we're alluding to here, what we're whispering of here, is a difference between kind of nominal dimensionality, the theoretical dimension that this system could occupy. It could occupy, in this case, Pius noted it first, any of 1,024 states. But realistically, the amount that the number that it's going to spend its time in, that it's really going to dwell in, that it's going to really, circle around, is vastly smaller than that. And this has to do with the intrinsic dimensionality, the typically much lower dimensional, much more simple, much more summarizable. We could characterize it in just 2 or 3 numbers for even a complex system like this one, or like the lynx hare system, that we could summarize its essential state in just a few numbers, like the number of hares and the number of lengths, even though the actual system is quite a lot more complex, has quite a lot more degrees of freedom, has quite a lot more, possibility of other factors going on. Okay, so here's the deal. This class has been speaking about dynamics, and it's particularly dwelt on nonlinear dynamics. These systems where they are, in a technical sense, complex, where the behavior is more than the sum of the parts. It's different from the sum of parts, where we can't simply take a system apart, parcel it neatly into susceptibles in this pile, infectives in those piles, or recovereds in those piles, simulate each separately and add the results together and get anything like what we would get from the world with them together. When we have these systems, and these systems lie at the heart of the world's foremost problems, these systems have some features that are thorny to control, but actually help ease our understanding of from what you might. We have coupling within these systems between different state variables. And I've repeated this several times, but you'll forgive me for emphasizing it again. The data about hares tells you a lot about what's going to happen with lynxes over the next little bit. We have tons of hares, tons and tons of hares. It's likely that the lynx population will be increasing. If the lynx population is dropping like crazy, it's probably because there's not many hares around. It tells us about the hares. We have these systems and they're so entangled that what's going on in one place whispers to us, sometimes quite loudly, about what's going on in another area. It encodes information. So some of you may remember this model. Some of you may recognize the structure of this model. This model is reflective of a stock flow model of which I've spoken, I've uttered at least 5 times in this presentation alone, and that we presented back when the snow was not yet blanketed upon the soil. He spoke of this model. What model is this that stands before us? I'm not talking about myself. I'm most certainly not a model. I don't go up on catalog. So so Pius. There is a first order delay associated with it. There's 2 first order delays that are in it. And so I will say you recognize some features of this, but this whole model has a certain name. And Eric, stock and flow. It is a stock and flow model. It's definitely a stock and flow model. So absolutely, you two are absolutely right for characterizing those features. But there was a certain context in which we simulated this model. X was something and Y was something else. Sorry? Well, there are derivatives here. Yeah, those are derivatives, absolutely. And I welcome your identification of those derivatives. Please make sure that everyone here remembers them for the final. Right? Jihan. Wolfen here. Links and hairs. Yeah. What's that?
It's a little here. That's just so obvious.
Well, we did introduce this model in its structure in several lectures. And X is hairs. Alpha is the growth rate of the hair population absent predation. Y are the links, and therefore there's a term flowing out of the hair that an outflow from hairs, reflecting the fact that links can eat hairs, and therefore X times Y. Each hair has a certain probability of beta on a per that will be caught by each links on a per unit time basis, or actually per links per unit time basis. Y is the links population. The outflow reflects the fact that lynxes naturally die on a certain basis, but their birth rate, the birth rate of lynx, which is gamma X, depends on their sustenance, how many hairs they can eat. Okay. I won't belabor this point, but what I want to highlight, it wouldn't be a bad thing to be familiar with the broad features of this model for coming events. I will just say that if you take a look at this model, let's take a look at a single component from this first equation here. I can actually solve that equation. That's an equation, right? I can actually solve it for y. Y is the number of links. I can say the number of links at a given point is equal to alpha x minus x dot, divided by beta x. Okay. And you could just do the necessary thing. X dot, bring the alpha x over onto that side. Or better yet, bring beta x of y to the other side, bring alpha x dot to this side, and divide it by beta x, right? And you get the value for y. What that's saying is, look, we can calculate the value of the number of links at any time based on this formula involving only what are x's in this formula? Can anyone say why are linkses? We're saying we can calculate the number of linkses right now in the population based on data only on y. What is x? Hairs. Based on data on hair. If we know the number of hairs and we know the rate of change, how quickly they're changing, we can calculate links. the number of links right now. Similarly, we could solve for the other equation, we could solve for x. We could get the number of hairs, calculate that based only on information on the number of links right now and the rate of change. So if links numbers, for example, are very high and are dropping quickly, then that's probably a sign the number of hairs is smaller than it would be if they were growing the number of links were growing very, very rapidly, and there's few links around. So the number of links tells us something about the number of hairs. If there's very few links around and the links numbers are growing quickly, that's a sign there's a lot of hairs. There's a lot of hairs around to support that growth. Conversely, if all we knew about hairs from the number of trapped hairs, for example, and their rate of change, that tells us something about the links population. If the number of hairs right now, for example, are dropping very quickly, so we have minus a very large negative quantity here, it's a sign that there must be a lot of links around. What I'm telling you, though, is showing that for this model of links and hairs, you can actually compute the number of hairs based on only information about links, or the number of links based on only information about hairs. Those two are that coupled that information about one, its value over time and its rate of change over time, will tell us the value for the other. Okay. So within these coupled systems, knowing about the value and the rate of change of one variable can tell us a world about the value for the others. There's so much information packed up in the number of hairs and its change over time, its rate of change, that it can speak to us about the value of the links population. The two are that coupled in these nonlinear dynamic systems. Same thing with Westnot. We don't have time to go into that as an example. Now that was from a model. That was talked about case for a model. But here's the thing. That is also true for data from the world. When we are dealing with these systems, these underlying systems, these thorny, complex, and often wicked systems that underlie some of the biggest challenges of the world, where the whole is greater than the sum of the parts, the same thing is true. Information about one piece of the system will tell us a lot about what's going on in other areas of the system. So within these systems, there's good reason to suspect that if we listen carefully enough about the few points, areas of the system where we actually have information, that we can actually learn a lot about the broader system. And it turns out that that's mathematically provable. There's something called Taken's embedded theorem. It's named after Floris Taken, a Dutch mathematician, who basically proved that if you have a system out there in the world, doesn't require any model of it, and you have data about this, you can reconstruct the state space, the underlying state space of the real system in the world. Or something basically that is the same as it, except it's kind of stretched and deformed, but it's not, it retains its topological structure. It retains its fundamental structure. Maybe stretched a little bit and pulled, but it's not disrupted, it's not torn in any way. Using just a single time series from that system. No, that time series has to be sampled. Frequently enough, it has to be certainly long enough. And it has to be analyzed in the right way. And specifically, these goggles that we put on are about what's called delay embedding. We perform a delay embedding. And delay embedding looks like, okay. So if we have a time series Y, so Y might have data over time on the number of COVID-19 cases, and maybe we have data from day 0, 10 cases, data from day 1, 2 cases, data from day 3, data from day 4, and so on. It's some time series of numbers, etc. Technically real time. If we were to take this, and for each time point, except those at the very end where this might not be possible because there's not enough data before it, and for each time point, we create a vector for that time, specific time that is the data at that time, that's y of t, and then data for some amount of time before that, say 1 day before that, and for 2 days before that, and for 3 days, tau, I'm using this day here, a single day. If for each point in time, we create that vector, so we have such a vector for day 100, and that has from the original time series, which is all these different values for different points in time, a reconstructed one. If we do it with n equal to 2, it would go like this. It would have the value for time 100, the vector for time 100. Time 100 has some value y of 100. The day before it some value y of 99. The day before it some value y of 98. This would be in our vector for day 100. The vector would have 3 components. N is 2, so we have n plus 1 components here. And what we have is 3 values. The value from that day, y of t minus 1, and y of t minus 2. And we do this for each day. We do it for day 101. We have a different value for it. 101, 100, and 99. Y of 99. And we do this for each day. We have a vector like that in each day. You could say, well, that's kind of weird. Like, why in the world would you do that? Why would you create a vector for each point in time? Isn't there so much overlap? I mean, after all, 100 is here, it'll be on the next one too. Like, what? Why would you do that? Well, you do it because you can take that data and put it into a space, and that will recreate the state space of the system that gave rise to. Let me show with an example, a classic example. So here's some data. By appearances, it's very entropic. You see some patterns, right? I mean, there's some apparent regularities. If I were to push you to say, like, what regularities do you see on this? You might say, well, it's kind of a bunch of high frequency oscillations. They kind of grow in magnitude, and then there's like a bigger one, and then they shrink, and then they kind of grow. But if I were to ask you to like tell me what comes next from this, right? If I said I have these observations from 3 points in a system, what's next for each of them. You'd have to think really hard, at least, right? It's quite hard. And as far as like broad regularities, like what's coming over, if I ask you to draw out what will be coming over the next 100 time points, that would be really hard, right? It just doesn't seem there's enough regularity, orderliness to it, enough systematic character. Well, what if I were to tell you that data actually came from a very orderly system? And that system is shown on the upper left, called the Lorenzo. All we're doing is we're observing data from 3 axes here of the Lorenzo tracking. Yeah, I'm giving a lecture here. If people want to hear you lecture, you could, volunteer a class for the university. So here we have an underlying system that's giving rise to it, and we have 3 axes of the system, and that's what I'm plotting up here. You can see the actual underlying system, the evolution of the system is actually quite structured. It has these 2 different modes that it can be in, and the system loops around this mode and then goes to another mode and then loops around this mode, etc. Now, we can kind of view this from different angles, the system, But here's the thing. The structure of that system can be understood from just one of those pieces of data over time. We can reconstruct the structure of this system. This shows it from one of these time embeddings. Here we're just doing it for n equal 1. So in other words, this is of length 2. We're observing x versus x minus 1. X versus x minus 1. And we're plotting this out. And what we see is actually something that mirrors the structure of the underlying system. It sort of recapitulates the basic connectivity, the basic features of that underlying system in a stretched way. And it turns out that a lot of time series that nominally look kind of hard to predict, puzzling, hard to know what they're going to do next. You're not sure what to make of them. You don't see any big patterns. They actually, if you plot them out with this right set of goggles like this, but more sophisticated yet, but it very much in that vein, you start to see these regularities. This is from just one time series for data from a infectious disease model. This is another lens on it. This is reconstructed state space from data from smartwatches, for example, collected, I believe it is on heart rate variability data. So we don't have time to go into this, but why would we do this? Why would we put on these goggles? I mean, it's kind of interesting. You can peer into the state space of the system, but why would you do that? Well, look, we're interested in understanding these systems that give rise to these phenomena, that are complex. And by so doing, you can actually study their structure. You can study their salient features in ways that we can build better models for them. We can build models that better reproduce their essential dynamics. We can assess their dimensionality, like how much information do we really need to summarize the system effectively? The connectedness. We can predict what's next on these sort of systems much more effectively. You try to predict the next evolution from something like this middle one, what value it's going to be next. Notice it's kind of going between these different modes, sometimes really short, sometimes actually fairly long, sometimes mid-sized. You're setting yourself up for a very difficult task. You actually recognize the underlying regularity of the system. You can do a vastly better job at predicting where it's going because you're describing it in the right coordinate systems, much as Copernicus, by reasoning about the heliocentric view of the solar system, realizing that, wait a minute, planets are all revolving around the sun. We should think about how they revolve relative to this sun. He could actually end up predicting far more effectively things like the occurrence of eclipses, or when a certain phenomenon involving Jupiter rising above the horizon in a certain location, etc. He could predict all these things, and ultimately you could use it to observe and keep track of time in a consistent way across different continents long before the invention of things like radio or ability to communicate. So it turns out, like, getting the right way of describing a system to build a good model of it can give you huge advantages. And these goggles provide this as a way of looking at very complex, seemingly complex data from the world and finding the hidden structure, looking at data that looks like this, where it's hard to make sense of it, and finding, aha, behind that is a simple, powerful, salient, and useful distinction, or a set of ways of understanding the system that allow us to build better models. Now, one thing I will note that Wade has actually done some wonderful work on is a use of this to actually understand in the world causally what's driving what. I mean, there's a lot of factors in the world that are correlated. They kind of, one's high when the other's high, or one's high when the other is low, and a lot of science is based on making observations of these correlations. In epidemiology, this is what so much of the field is about, noting these associations between things, and that's important, and it's worthwhile, and it can give some important insights and raise concerns about disparities. But at the end of the day, we often don't, in general, we don't, through that, know what's driving what. If you try to understand certain phenomena in the world that may be highly correlated, you could have very different implications if A is causing B, or B is causing A, or if there's a C causing both A and B to behave that way. Well, it turns out one of the things you can do with this reconstruction is try to identify what is driving what. And you can assess critically, are certain things driving the system, or are they mere correlations and there's something else driving them? But A is not driving B, but maybe some C is driving both A and B in ways that look highly correlated. So you can do the state-space reconstruction, and by comparing the signatures that come out of these systems, at first blush, you won't know how to make sense of this, but just suffice it to say that there's a big difference if you put on these lenses between how a system looks if A and B are merely associated, if there's no A is not causing B, versus if A is causing B over here on the right. The shape of these, and this is actually indirect causality in the middle. This is direct causality on the right. This is no causality on the left. So using data from the world, none of this involves a model, right? Like this is not about an agent-based model, like building an agent-based model to tell us this. This is about observing data from the world. Now, we can study this with data from a model to critically assess how effectively it can perform and so on. But at the end of the day, we can do these sort of analyses with data from the world as well. And that's where some real value comes in. So time is short. And I don't have time to go any further into this. I'll just say that in this world, which is seeing so much expansion of possibilities and so many expansions of dangers also involving the rise of data science, of big data, rise of effective machine learning tools. You may wonder where dynamic modeling fits in. Where are the tools of system science fit in? Well, the tools of system science are critical for deriving insights into many phenomena involving complex systems when we wish to pursue a data science lens. When we're trying to understand data science, when we're trying to understand how to pursue data science, how to use machine learning most effectively, it behooves us to recognize that we're often dealing with underlying systems where we have different faces of the same underlying system, where systems are coupled. And we can put on those lenses inspired by system science that came out of system science to get especially powerful views of these systems in the world. Powerful and effective views. These highly coupled systems beg for an understanding that reflects the fact that they are complex systems. And we can go quite far with that. The enterprise of systems data science, and I've just alluded to one portion of it, there's many other portions, collectively give us a way of working together system science tools on the one hand, including simulation modeling as a key component of that toolbox, with data science techniques, including machine learning, including the use of big data. But they help us use those much more effectively and help us use them to ask about what if questions where we don't have data. So much of the data science enterprise is geared towards questions where we have lots of data. And all of that's excellent. But when we go off-road, when we leave the path that we've been on, and we enact new interventions. Perhaps we've been in COVID-19 pandemic and been looking at the patterns and the relationship between cases and the number of deaths. And now we have vaccines introduced. We have dexamethasone, and a new drug that comes out. Or we have new clinical practice guidelines. Those change the data generating process. Those will alter the associations. Those will alter the patterns we analyze with data science techniques. And we need system science tools to help guide us not only to the techniques to study these systems, but also the techniques for asking about what will change when we put in place interventions where we don't have data to guide us directly. Those are all the comments I have on this front. We have only with us yet 4 minutes.